this is the fourth lesson in the binary bits and bobs unit, and today we're going to be looking at representing images with binary. So let's have a look at what an image file might look like if we were able to actually look at the data within it. So an image file is made up of binary. Everything that is trying to be represented on a computer system has to be converted into binary for the computer to be able to process it. So if we had a look at this picture here, you can see that it just looks like a load of ones and zeros. Now if I was to say that black was 1 and a 0 meant white, then perhaps we would be able to start to have an idea as to how this picture could form. We'll come back to it in a minute. So in this lesson, we're going to, I've already said, remember that everything that can be represented in a computer, whether it's numbers, characters, images or sound, has to be done so in binary. We're going to understand what a bitmap image is and the idea that it's made up of pixels. And we're going to understand how binary is used to represent the shades and the colors of images and therefore represent each of the pixels within an image. So this here is the image that we saw in that first slide. Only the difference is that where there was a 1, it now is a black square, and where it was a 0, it's now a white square. And you can see it's a little alien from an old arcade game. There's the data that we saw before, and there's the image that it represents. So we've already discussed this earlier, but computers only deal with zeros and ones. Computers are made up of switches. They can only be in one of two states. So therefore, computers can only really represent two things. Whenever a computer represents anything, whether it's numbers or characters like we saw in the last lesson, it has to do so in binary, and it's exactly the same with images. Images are represented in binary, and we've just seen an example of this. So a bitmap image, they're made up of rows of dots called pixels. Now a pixel is short for picture element. Now every pixel that you have on a computer screen is represented by a binary number. And that binary number will represent the shade or the color of that pixel. So behind the scenes, this 1-bit image, which is an image which every pixel has just 1 bit to define its color, so that's either a 1 or a 0. Behind the scenes, this 1-bit image is in fact a series of numbers, as we've seen. So bitmap files, they're made up of strings of binary numbers, as we just saw on that last slide. The computer, what it will do, it will read the binary numbers in that file, and in a 1-bit image, it will look at each binary digit in turn. Now, in a black and white bitmap, when the computer reads a 0, it will tell the monitor to make that matching pixel white. And then it will move on to the next digit in that binary file. And if it reads a 1, it tells the monitor to make the next pixel on the screen a black. And so on and so forth until an image is created. Now, of course, computer screens are made up of colors. So in a colored bitmap, what we would need is a longer binary number to represent each pixel. If we only use 1 bit, then it can only be a 1 or a 0. That's only 2 possible colors, in which case it would be a black or a white. But if we have more binary numbers to represent each of the pixels, then we can have more combinations of these zeros and ones, and therefore we can represent more colors. So in a colored bitmap, the computer splits the binary file of all those zeros and ones into 8-bit long binary numbers. So the computer will read each 8-bit number in turn. And each 8-bit binary number will represent a different color. So each time the computer reads an 8-bit binary number, it looks up the color that that number represents, tells the monitor to display that matching pixel, that particular color. Now with 8 bits, you can only represent 256 different colors, and that's not fantastic. If we look at a 24-bit true color display, what you'll find is that we have 24 bits to represent each pixel. And those 24 bits are split up into blue, green and red, or different shades of blue, different shades of green, different shades of red. And they will combine to generate a different color. So in true color bitmap file, longer binary numbers represent the colors. The longer the number, the more combinations of colors the number can represent, and therefore the better quality in terms of the color depth the picture will be. So in summary, bitmap images are made up of rows of dots called pixels. Each pixel is represented by a binary number. A black and white image is represented by a series of zeros and ones, which in what we mean by that is that if you were to look at the data within that file, the computer would read each individual bit in turn to determine the color of each pixel. In a color image, it's made up of a series of different colored pixels, and each color has its own binary number, which will be longer than a single bit. It might be a 4-bit number, it might be 8-bit, and as we saw on true color displays, it might be 24 bits for each particular pixel. As images get more colorful, longer binary numbers are needed so that a bigger combination of colors can be shown. So here we've got an example of a 4-bit bitmap. That means that 4 bits are used to define each pixel, the color of each pixel. Now what we've got is the different binary codes for the different colors here. So if we wanted to know what color this pixel would be, we can see that it's 1111. The color for 1111 is white. Over here we've got the binary number 1011, and if we look at 1011, we'll see that it defines the color, it's defined by the color yellow. So if you could look at each of the colors for each of those pixels and color them in, this particular binary image file would actually represent a pretty awful looking Christmas tree.